Guys, I'm sorry I'm not here today, but I made these just quick review notes over the PowerPoint and the information that you needed. Please be good for Mr. Schultz. He is such a nice man to do this for me, so please be on your best behavior. We're going to start with valence electrons. We've talked about valence electrons before, but remember, valence electrons are electrons in the outermost energy level. So if I have an element like sodium, right? We all know that sodium is 1s2, 2s2, 2p6, 3s1. And so the outermost energy level is this third energy level, and there is one electron there. So sodium has one valence electron. Having that one valence electron is the same as its entire family because all the alkali metals end in S1, therefore they all have one valence electron. It's important to remember that when we're counting valence electrons, that we only count S and P electrons. D and F are in those weird shapes, and those shapes hide those electrons from being accessible in bonding, and therefore they are not involved when we talk about valence electrons. Okay, so just S and P when it comes to valence electrons. So they make a pattern on the periodic table. So I'm going to draw a beautiful periodic table here. It's a little exaggerated because I write kind of big, but everyone in group 1, just like sodium, has one valence electron. Everybody in group 2 has 2. We skip the transition metals because they're in that D sublevel. Everybody in group 13 has 3, 14 is 4, 15 is 5, 16 has 6, the halogens have 7, and the noble gases have 8, except helium, right? He's super special, and he only has 2 electrons. Even though he's in the noble gas family, he doesn't have 8 valence electrons. He only has 2. We use valence electrons to draw Lewis dot diagrams. And so one scientist named Lewis, right? We always love these scientist names, loved electrons. And so Lewis made his own way. He liked to organize valence electrons into dot diagrams. So Lewis dot diagrams just show the number of valence electrons. And they do so just kind of like we do our orbital diagram. So you'll have some sort of symbol. We'll say X. And then there are regions of space, right, to the top, to the right, bottom, and left of that element. Those are where you would put the dots, right? It's a dot diagram, and you can fill those dots up. One of those dots is an S, and 3 of those sets of dots are like a P orbital. So for example, let's do carbon as I write calcium. Let's do calcium because I already wrote Ca by accident. So calcium we know is 4s2, and so we would draw our 2 dots right there on the top of calcium. All right, now let's do carbon. Carbon is 2s2, 2p2, but we want to separate these because, like in the P, you want to only pair after you have filled them all. So carbon would be 2s2 and then 2p2, but separate those dots. If we were to do oxygen, right, oxygen is 2s2, 2p4, and that fourth one would go back in pair. I hope that makes sense to you about how those dots work. The number of valence electrons, so oxygen has 6, you have to show 6 dots around that oxygen. What you cannot do is say like chlorine, 1, 2, 3, 4, 5, 6, 7, all in a line. That is not proper Lewis dot diagram, so please don't do that. Make sure they're in pairs because they are paired up in orbitals, and that you separate them when needed. Thank you. The next thing we're going to talk about is oxidation numbers. Oxidation numbers, oxidation number. That does not show up very well. Let's try a different color. That looks a little better. Okay. So an oxidation number is the charge an element will become to satisfy the octet rule. Well, then your question should be, well, then what's the octet rule, Miss Heverdays? The octet rule states that atoms are more stable if they have a full outer shell of electrons, if they look like a noble gas. So noble gases are something S2, something P6, and 2 plus 6 is 8. Oct means 8, so that's where we get the octet rule name. I like how you could not see that while I was doing that. So I'll just go over that one more time. Oxidation numbers are the charge an element will become to satisfy the octet rule. Atoms are more stable if they have a full outer shell of electrons, and they have a full noble gas notation. So they have NS2 and NP6, a full outer shell of S and P. Remember, for valence electrons and for bonding, we only care about S and P, and that equals 8, and we call that the octet rule. Just like valence electrons, this forms a pattern on the periodic table. So everyone in group 1 has one valence electron, right? If we go back to the top, everyone has one valence electron here. And so if you have one valence electron and you need to get to 8, my question is it easier to lose that 1 or to gain 7? You should be saying lose 1, Miss Heverdays. So if you lose an electron, you become a +1 charge. If you have 2, it's easier to lose 2 than to gain 6, and so your oxidation number becomes +2. If you have 3, it's easier to lose 3 than to gain 5, so losing makes you a cation. Cats get lost, and that gives you a +3 oxidation number. Now 4 is tricky. You could do either, right, plus or minus 4, but what they really like is covalent bonding, and we'll talk more about that in our next unit when we talk about bonding. If you have 5 valence electrons, now we're going to switch. If you have 5, is it easier for you to lose 5 or to gain 3? Well, if you gain 3 electrons, you become a -3 charge. If you have 6, it's easier to gain 2 than to lose all 6, so you become a -2, a -1, and the noble gas family has an oxidation number of 0 because they do not form a charge. They're already satisfied by the octet rule. And so I just feel like a little happy face. They're already happy just the way they are. So those are oxidation numbers. So if I ask you, what's the oxidation of aluminum? You can quickly look at the periodic table and say aluminum has a +3 oxidation. It needed to lose 3 electrons to have a full outer shell and look like a noble gas. Our word for looking like a noble gas is another special vocab word that you need to know, and it is called isoelectric. Our prefix iso means the same. Electric, think electrons. So these have the same number of electrons. Aluminum with a +3 charge, if aluminum has 13 protons, I'll go ahead and put mass number there, and a +3 charge, protons minus charge, 13 minus a +3, gives me 10 electrons. That means that aluminum with a +3 charge is isoelectric with neon, because neon also has 10 electrons. It has no charge, so if it has 10 protons, it has 10 electrons. And so they have the same number of electrons. We call those isoelectric. That's a good vocab word to have. We use this concept of isoelectric species to identify ionic size. So yesterday we talked about atomic size with our other trends, but now we're going to talk about ionic size. So ionic size is the size of the ion. And they're slightly different than that of the atom. But if we think about that force of attraction, that Coulombic attraction, this will make complete sense. So if we look at aluminum with a +3 charge and neon, and let's do magnesium as well, right? All three of these are isoelectric. Aluminum has 13. Let's do a -1 too. Hold on. Let's do fluorine with a -1. All four of these, have the same number of electrons. So 13 plus 3 is 10 electrons. Neon has no charge. It has 10 electrons. Magnesium plus 2, 12 plus 2 gives me 10 electrons. And fluorine is number 9, but it's going to gain an electron, and so 9 minus a -1 also is 10 electrons. When thinking about their size, you also need to think about their nucleus and their number of protons, just like we did with atomic size. So aluminum has 13 protons, neon has 10 protons, magnesium has 12 protons, and fluorine has 9 protons. Based on this information, which of these ions do you think would be the largest? I'm going to give you a minute to think about it. Remember Coulombic attraction, if I increase my number of protons, I'm going to increase the force of attraction, and that's going to pull electrons in tighter. Okay? So the largest one, and this would make them smaller, decrease size. So our largest one would be fluorine, because fluorine has the least amount of attraction because it has the least amount of protons in its nucleus. This makes aluminum the smallest. So this one's the smallest of these four, and fluorine would be the largest. And that should make sense based on the force of attraction in the nucleus pulling on those valence electrons. Now I want you to try your worksheet, and if you have any questions, you can always come and see me in the morning. Okay, thank you.